There we go. That did it. All right. So today we begin in earnest. I have two goals for today. The first goal is to discuss cosines in all their infinite glory. And then hopefully at the end of class we'll have a little time to discuss Euler's formula. So basically the name of the game this semester is cosines. Everything's getting turned into a cosine. So we got to start really by making sure we understand what we're talking about. So we discussed very briefly on Monday sort of how to measure the period of a cosine and the frequency and so on. So if you remember the basic rules, a cosine has a period, which we denote by capital T, and that is in units of seconds. Some units of time, usually seconds. Okay. If we take the reciprocal of that, we get in hertz. So frequency in hertz is the reciprocal of the period, which is in units of hertz. Is that big enough? Can you guys see that? That's cool. Okay. All right. So another way of saying hertz is cycles per second. All right. So if a signal goes up and down and up and down and up and down like 4 times in a second, we say it has a frequency of 4 hertz. Okay. And if it goes up and down 4 times in a second, what's its period? 0.25. That's right. If it does 4 oscillations in 1 second, then each oscillation must take a quarter of a second. And that's exactly this relationship, right? If you take the reciprocal of period, you get frequency. If you take the reciprocal of frequency, you get your period back. Okay. Then the last bit we talked about with frequency was that we decided that every oscillation is worth 2 pi radians. Okay. Therefore, if your signal oscillates at a frequency of f cycles per second, it also oscillates with a frequency of, actually, where's my 2 pi f radians per second. So that's sort of like the trifecta that we want to get used to. So there's another form for frequency, so a unit conversion. Each cycle, f, is worth 2 pi radians. So we can either say f hertz, or completely equivalently, we can say omega equals 2 pi f radians per second. Okay, those are 2 units of frequency. All right, don't talk about degrees. They're dead to you. Okay, we're going to be talking a lot about phases. Phase is always measured in radians, right? Degrees is for like high school. Okay, engineers use radians. Okay, so let me write a cosine. So the general expression for a cosine might look something like this. X of t equals, you can say it one of 2 ways. You can either say cosine 2 pi ft, or you can say cosine of omega t. That's just like the generic expression for a cosine. So let's see how quickly this becomes complicated. Suppose I asked you to plot x of t equals cosine 6t. I'd like to get a plot of that. Now I know you've all done this before because you've all taken calc and pre-calc and pre-pre-calc or whatever they make you take. So I know you've seen this before, but it's my job to make sure we dot the i's and cross the t's so that all this makes sense, because it's going to get real hard real fast, and if this stuff is not like super comfortable, the stuff that comes after it's going to be awful. Okay, so we got to make sure that this, we got our heads wrapped around this. So I want to plot this. So it seemed to me that if I want to plot this, probably I need to know the frequency of the period or something. So what can I deduce from this expression? Can I deduce the period, the frequency in hertz, or the frequency in radians per second?
Could you find the angular frequency in radians per second?
Good. So what is my frequency in radians per second? 6. Good, right? You just do pattern matching, right? if I express my cosine as omega t, then in this case, my frequency is, omega has to be 6 in this case. 6 rads per second. Okay, that's a start. Now what do I need to do before I can plot that? Right, I still need to know either the frequency in hertz or the period in seconds. Okay, so how can let's see, I guess a natural first step would be to convert that to hertz. So how do I do that? Good, I remember the expression that omega, which equals 6 in this case, also has to equal 2 pi f. So I can solve for f. So f is going to equal, what is it going to be? Looks like 6 over 2 pi, which is equal to 3 over pi. I'm going to leave it like that for the time being. And finally, I get my period, which is, period is the reciprocal of that. 1 over f, which equals pi over 3 seconds. How much is pi over 3 seconds? It's pretty close to 1. Engineers are pretty good at squinting and, you know, I'm not gonna lose a lot of sleep over this, okay? I'm just gonna draw it pretty close to 1. So if I were to draw that, I would draw for you a cosine whose period is, I mean, if I wanted to do it exactly right, I would say that the period is pi over 3 seconds. Okay? So that's pretty easy, right? So we could play this game over and over again. I could come to you and say, you know, cosine of 10 pi t, cosine of 15 t, cosine of whatever t, and you could plot it. Sound good? Okay, so that's a fun game to play. Except not really. That's my fault. It's embarrassing. There's a giant hole in his pocket. The iPhone just wiped out. I don't know whether it's easier to go up or down. This is embarrassing. Let's see here. I think I can fish it out. There we go. Switch pockets. Okay. All right. Sorry about that. Okay. So I'm actually impressed it stayed in there as long as it did. All right. So let's make it a little more complicated. Suppose your jerk of a professor came along and said, let's see. Four t minus 2. What? Yes?
Isn't the minus 2 a phase shift?
The minus 2 is a phase shift. Okay, so help me plot it.
This is 4 equals 2 pi f, up for f.
Okay. So my frequency, so let's start. So it turns out this isn't exactly a complete expression, right? Because it turns out I can stick in like a minus next to it. So we'll deal with that minus in a second. But you're right. So the first thing we need to figure out is the frequency, right? Either way, we need to know the frequency. And in this case, the frequency is just 4, right? We still read it the same way. So what's my period going to be? Let's see. My frequency is omega over 2 pi. And therefore my period is 2 pi over 4, which is pi over 2, which is about 1.5. 1.5 amperes, henries, seconds, right? Don't leave me high and dry, right? You got to get your units on there. You might think it's obvious, but I don't know that you know unless you put the units there. Okay, so should I just draw something that has a frequency of pi over 2 seconds? I still got to deal with this business, right? Okay, so how do I deal with that?
Subtract 2.
Shift, sorry?
Subtract 2 from whatever number we have.
From this number?
You have to divide it by control the frequency minus 2 from the thing, and then you just shift the graph.
Okay, can we agree that it's a shift, a time shift? We all agree it's a time shift. Okay, so all we have to negotiate is how much time shift?
It's 2 in comparison to the so you got to divide it by 4.
I don't think we got to divide it.
2 seconds to the right.
Okay, so this is tricky. Okay, now so I love this problem because it's so deceptively simple. Like, it's easy, right? We've done this in high school, and yet reasonable people are disagreeing about it. Yes?
Divide by the frequency.
Okay, why are we dividing by the frequency?
Because you want it to be in radians.
Ah, good.
Wait, that's in degrees?
Yeah, because it has to be unitless to cosine.
Ah.
Everything has to come out as radians in such a cosine.
Let me...
Is it 2 radians or degrees right now?
It's just 2.
It's just 2.
Well, that's a great question. What is this?
Can we even talk about what unit that is? Did I lose the mic?
Okay, so some fascinating questions. What is the units of this 2? Okay, we have votes for none.
No, that's in seconds.
We have votes for radians. We have votes for seconds.
It's in seconds.
Because 4 is omega, which is radians per second. The seconds cancel out with t, and we're subtracting, so radians minus radians is still radians.
Yes.
It's radians, but radians are kind of, they're a natural unit, so that you could say it has no units.
All right, so that's a technical argument. But okay, so let's hold that thought for a second. I think the best thing we can argue at this point is that we know the units of 4. What's that? Radians per second. And we're multiplying it by seconds. So this has got to be radians. Radians per second times seconds. The seconds cancel. You're left with radians. Now you can only subtract 2 like things from each other. So this better be radians. Okay, so I agree that that's in radians. So are we going to shift it to the right by 2 radians? How do we shift it to the right by 2 radians? Okay, well, we know a minus sign always shifts things to the right. Right? I mean, we learned in, I don't know, pre-arithmetic or whatever it is, that if you've got a function f of t, okay, and then you have a function f of t minus some value, what's the relationship between those 2 functions if you were to plot them? Right. This is shifted to the right. Right shift by t units. Okay. So we can agree there's going to be a right shift. But we're agreeing that the units is in radians. And I need it to be in seconds, so I know how many seconds to shift it to the right by. So let me give you some tools to kind of think your way through this. All right. So first thing is this. Can we all agree that, so we know how, like, usually when there's no phase shift, a cosine starts over here at 1, right? So we all know that cosine of 0 equals 1. Is that true? So let's look at this. This cosine is going to start when all the stuff inside these parentheses equals 0, right? Because that's where cosines start, when cosine of 0 equals 1. So what value of t is it going to be the case such that 4t minus 2 equals 0? It's 1/2, right? If I solve for t, I get 1/2. So in other words, for this current plot that we're negotiating, if I come out to t equals 1/2 and plug in 1/2 for t, I'll get 4 times 1/2 is 2. 2 minus 2 is 0. Cosine of 0 is 1. So I can almost imagine that my cosine will start there. And from here, it will follow a natural course where the frequency is, where the period is pi over 2 seconds. So what's this number going to be?
1/2 plus pi.
Right. It's going to be your original 1/2 plus the period, which is pi over 2. Okay, get your calculator out, right? Nobody cares about what the actual number is. I mean, pi over 2 is like 1.5. A half is a half, so 1.5 plus a half is, it's in the neighborhood of 2.
So to get the phase shift, we can just solve for 0.
Well, this is sort of like your street fighting technique. Okay, this is like when you're just left to your wits and your defenses, and you've got to do whatever you can to make it work, right? This is like the dirty, I couldn't remember the formula approach. But there is a cleaner way to do it. So let's examine the cleaner way. Right. There's two ways of doing it. Probably the easiest way is to say this. The generic formula is x of t equals cosine of omega t minus phi. Okay, so in other words, I'm just extending our generic. This was without a phase shift. Now I'm adding a phase shift. Okay, so this is really your generic cosine. Well, there's actually one more change we're going to make in a second, but we'll get to that. All right, so we need to know how much to shift it by. I would argue we could do the following. If we took this cosine and rewrote it as, I'm going to factor the omega out of both expressions here. So I'm going to say omega times t minus phi over omega. Now, look what I did over here. You remember this conversation? If you take your time unit and subtract, if you subtract something off your time unit, that's your phase shift in right. That's what I've done here. Because what's the units of phi? Radians. Divided by radians per second. That's like multiplying by seconds per radians. The radians cancel. You're left with seconds. So this is the amount of seconds you're going to shift it to the right by. Generally speaking, I guess if you wanted to, like instead of writing cosines like this, you could equivalently write them like omega t minus t shift. I can't use capital T because that's used for something else already. I could write it like this. And this is basically saying the same thing, but nobody ever does it this way. People always express their shift in terms of radians, not in terms of seconds. And I think the reasons for that will kind of become a little bit more apparent as we move forward. So we're always going to express our phase shift in radians per second. So let's just erase that. It's a distraction. What do you think? Told you, right? It looks simple, but it gets ugly. Questions? No? You guys all right? Yeah.
So how would we graph it doing that second way? Like where would you start from?
From this way?
Yeah, from that way, using that approach.
Well, this is it. That's basically what we did, right? What was our phi over here? Our phi was 2. Our omega was 4. So your time shift is phi over omega, 1/2.
Okay.
That's basically what we did.
Okay.
Right? That's a good question. I probably should have. I could have explained that better. Right? The street fighting approach is basically the same as what the formula does. So I like having both approaches. Like in my own mind, when I try to organize my thoughts on this kind of engineering, it's always good to have the formula, but invariably you forget the formula, and it's nice to have like an intuitive way to figure it out kind of thing. So it's the more ways you have, the easier it is to get back into it. So there we go, time shifts. You want to try another one?
Sure.
Let's try another one. What if we did x of t equals cosine, here, let's stick a 3 out front. 3 cosine, let's see, 8 pi t minus pi over 3. I mean, the short answer is you get out your calculator and do it, right? That's how you plot it. But, you know, I realize that you're never going to have a job where people hire you to draw cosines. I get that. But we got to build an intuitive understanding of how these things are built, because everything else is kind of built on this. So if the brick at the bottom isn't solid, everything else will crumble eventually. Okay, so what's the first thing I need to know? All right, we know the magnitude. Magnitude's 3. That's easy. We can change that at the end just by labeling how big the cosine is, right? We'll get to the 3 at the very end. First thing we need is the frequency, or the period rather. So I want to know my period. How can I get to that? Right, so what's my frequency? 8 pi? 8 pi t? Just 8 pi. Leave the t out of this. Is that omega or is that f? Good, because it's always omega t. Okay, so omega equals 8 pi rads per second, which means that my frequency in hertz is omega over 2 pi, always, which is 4 hertz. And therefore my period is 1/4 of a second. I could write 0.25 seconds. I could write 250 milliseconds. Okay, it's all the same business. Okay, so I know the frequency of the signal. Very nice. Next thing I need to know is phase shift. All right. So how can I work out the phase shift? Is it a phase shift to the left or the right? Shift to the right. We know it's a shift to the right because of the minus sign. Okay, so how far am I shifting it to the right?
It's going to be 1 to 1 by 3 radians.
Okay, well just, if all else fails, plug and chug, right? So what's my phi is pi over 3. My omega is 8 pi. Therefore, my time shift is pi over 3 divided by 8 pi, 1 over 24. One over 24 seconds. Let's see. 1 over 24. 1 over 2 is a half. 1 over 4 is a quarter. 1 over 8 is 0.125. And then 1/3 of 0.125 would give me 3/8 of 24. So 1/3 of 0.125 would be 0.041. 0.041 seconds. Is that roughly correct? You guys just not sitting there with your calculators out?
I got 0.04166.
All right, there you go. Screw the 0.66666. All right, close enough. All right. I'm a big fan of being able to do those kinds of numbers in your head, if only because I find half as often as not people mistype things in their calculator, and it's nice to at least have a sanity check. So like, hey, that number doesn't make any sense. Right? Essentially, the number I did in my head is I figured that a 24th is equal to an 1/8 times a 1/3. Right? I know an 1/8. I know a quarter is 0.25. An 1/8 is half of that. So an 1/8 is 0.125. And then I got to take a 1/3 of that. So what's a 1/3 of a 12? What's a 1/3 of 12 is 4. A 1/3 of that. A 1/3 of 5 is 1 point. Oh, it's actually 1.66. Yeah, I could have gotten the 0.66. I apologize. There you go. So slap a decimal point in there and you're off to the races. Okay, so we're ready to plot this thing now. Now, so my frequency is, so my period is a quarter, and all right, so I can basically draw it like this. So this number is what? That's the shift to the right, 1 over 24. And what's this number going to be? Actually, let's start with this. What's this number going to be?
It's going to be 1/4.
That's the period. A quarter second. And therefore, this number is going to be, right, it's whatever the sum of those two is, right? Let's see, a 24th plus a quarter, 6, 7 over 24 seconds. Somebody already said that. Okay? Nice. Oh, now we got to deal with the 3. How do we, what does this 3 tell me? Amplitude. 3 minus 3. Ta-da! Now, let's pull just a little bit more meat out of this. There's a couple things I want you to notice. So, my phase shift was pi over 3 radians. Is that correct? One cycle is how many radians? 2 pi. So if one cycle is 2 pi radians, then how many cycles is pi over 3 radians? Right, remember cross multiplying? Remember they actually taught you that for a reason. 1 times a third divided by, 1 times pi over 3 divided by 2 pi gives you 1/6 of a cycle. So, how many cycles to the right do we shift our cosine? 1/6 of a cycle. Does that make sense? It does, because how long is one cycle in this for this cosine? My period is 1/4 of a second. And I'm to the shifted to the right by 1/6 of a cycle. So what is 1/6 of a quarter? 1 over 24. Is that how many seconds we shifted it to the right? It is. Okay. So it all works out. Because it has to work out, because there's only one right answer. Okay? We shifted it to the right by 1/6 of a cycle. Questions? No? All right. Well, this is fun. Okay, so let's get back to, let's start to put this in context a little bit, why we're talking about these cosines and why the phase is so important. I'm going to leave all of this up here, except for, sorry, I'm going to take all this off, rather, except for the original cosine. So, just for the sake of argument, I'm going to do some more. Remember those plots that you guys were arguing with me on Monday, like what goes on the y-axis? I'm going to draw more of those. So let's say I come to you and I say x of t equals cosine of 8 pi t. So we've done this one, basically. It's basically just the same as this, but without the phase shift to the amplitude. So in this case, my frequency is it still 4 hertz? It is. Okay. So if I said to you, instead of saying, please plot this versus time, which we've just done, what if I said to you, let's plot this versus frequency? Okay. So we would draw this plot, or something close to this. So I'd come to you and I'd say, all right, is there any cosine at frequency 0 hertz? No. Is there any cosine at frequency 1 hertz in this plot? No. So on and so forth. What's the only cosine where there is stuff? 4 hertz. Okay. So what I would draw for you is a single peak at 4 hertz. Okay. So let me just leave that. That's as much as I care to plot that right now. Now, let me come and draw for you, let's have another function, y of t, which is equal to 3 cosine 8 pi t. And I say plot that in the frequency domain. Let's plot that versus frequency. What do you think would be the difference between the frequency plot for x and the frequency plot for y? Not that, sorry, behind you. Yeah.
It's going to be, y is going to be 3 times the amplitude.
Yeah, exactly. That's the only point I want to make. Like, if this stick has a height of 1 for x, then when I draw the plot for y, it's still only got energy at 4 hertz. But now, whatever that stick is, it better be 3 times bigger than this stick was. Okay, because there's 3 times more cosine at 4 hertz.
So the y-axis is just going to be the amplitude of the...
Sort of. It's going to be a little bit more complicated, but basically that's right. Okay, now, okay, I guess I'm going to have to change this to z now. Sorry. Okay, now I want to draw my plot for z. So this is my plot for x. This is my plot for y. Now I want to draw a frequency plot for z. It's the same as the y plot. But that's weird though, right? Because they're not the same function. Like, it should be the case that if I show you this plot, remember how we said that you can take a certain kind of information and you can express it either versus time or versus frequency. And it's like the same information contained. So if you know time, you should be able to get the frequency plot. And if you know frequency, you should be able to get the time plot. So my question for you is this. If this was in fact also the plot for z, that doesn't make any sense. Because if I showed you this plot, how would you know whether I was talking about this function or this function? Right? Yes?
Should be the amplitude 0?
Why is the amplitude 0?
No, the y-axis.
Yes?
Right? Shouldn't that be the amplitude at 0?
Amplitude at 0 time or 0 frequency?
What 0? 0 time.
But this axis is frequency.
Yeah.
So in essence, what this plot answers, we're going to talk a ton more about this. I'm just kind of trying to foreshadow the future. Hold on just a second. What this plot says is, like, let's say this is f equals 0. This question says, what this basically says is, does your function contain any, like, is there also a term that says plus cosine 0t? It basically says, is there anything here? And the answer is no, there's not. It's 0. There is no energy at 0 hertz. So I'm going to draw a 0 there. Right? Is there anything at 1 hertz in my function? No, there's not. So there's a 0 corresponding to 1 hertz. In fact, for all the frequencies I could think of, they are 0. The only one which isn't 0 is this guy. And that's what that plot tells me. But that doesn't get me back to my main problem. Yes?
So the first one we express it in terms of frequency and amplitude, right?
Yeah.
And the second one is the same.
Frequency and amplitude.
But the z part has a phase shift.
Uh-huh.
How do we show a phase shift with frequency and amplitude graph?
We need another graph! Exactly. We need another graph. There's no way out of it. We need another graph. So for the rest of the semester, you're going to be juggling 2 graphs. Yes?
So if you only have the magnitude plot, then you don't know anything about the phase?
Correct. The magnitude plot alone tells you nothing about phase. They are independent of each other. Okay? So therefore, in order to paint the complete picture, you not only need a frequency plot, a magnitude plot, but you also need a phase plot. So for example, in this case, I can't just show you this for x. I also have to show you, it'll also be versus frequency, but now my y-axis won't be magnitude, it will be phase. And what is my phase at 4 hertz for the plot of x? In this case, it'll be, remember, it's minus phi. What's my phi? 0. So in this case, I would draw a 0. At 4 hertz, I'd put a 0. What about for my y plot? Same deal. What about for my z plot? Now we have phase. Okay, so for my z plot, it's going to have the same magnitude as y, but for the phase, what's my phase going to be at 4 hertz? Yes, actually my phase doesn't even vary with frequency. My phase is just constant. At all frequencies, I've got a phase of pi over 3, but I'll just draw it at the one frequency so we don't get too confused. Minus pi over 3. Sorry, it's hard to draw down there. Crap, we get confused with this every semester. Yeah, we will do, no, it's going to be a minus. No, it is going to be a plus. Sorry, it's a plus. It's a plus, sorry. I reserve the rate, I got to go back and check my notes to make sure I'm consistent with whatever I've put in the book. But I think you're right, that is going to be,
Pretty sure it's minus in the book. So.
it goes minus in the book.
It would be a plus here, because you say that cosine is omega t minus whatever.
The minus just show the direction of the shift.
No, hold on. Let me just check. It's, okay.
Minus in the cosine, it's minus on the graph.
Right. So the thing is, it's as long as it's consistent with your definition of the cosine, it doesn't matter. The trick is just to be consistent, right? It's right both ways as long as you're consistent with your cosine. And since I wrote the book about 2 years ago, I'm going to have to just double check to see which convention I used when I wrote it. So let me check.
What do you mean consistent with the cosine?
Yeah, I use plus. Okay, so this. Okay, so here's what I mean. I could define cosine in one of two ways. I could either say your generic cosine is going to be omega t plus phi, or I could say cosine of omega t minus phi is the generic cosine. Either one is okay. Either one, it doesn't really make a difference. All right. In the book, I've used this form. Okay, and that's the one we'll stick with in lecture so that we're not making things worse than it is. If I defined it this way, then for the example I'm using, what's my value of phi? Minus pi over 3. If I define it this way, what's my value of phi? Positive pi over 3. It doesn't matter that it's the same function, right? It's still 8 pi t minus minus pi over 3. It's the same thing. It's just a naming convention. Okay, so I guess because of the way I wrote it on the board, well, we're going to stick with this naming. We're going to stick with what's in the book. So in this case, it really is true that it's minus pi over 3. I'll stick with my original answer.
That's for Z, the one down.
That's for Z, right. So this is the phase plot for Y. This is the phase plot for Z. And it turns out that this is the magnitude plot for Y. It's also the magnitude plot for Z. So the moral of this story is you always need two plots, one for magnitude, one for phase. Yes?
I'm looking at your book here.
Yes?
It early introduced that in complex conjugate. The phase there's
Yeah. We'll get to the complex conjugate stuff. I'm just trying to motivate the concept that you need two plots. Right? But when we get to the complex conjugates, we're still going to need two plots. One for magnitude, one for phase. Yes?
Are these basically like Bode plots, or?
No.
You know, the difference being that Bode plots are logarithmic.
No. Bode plots refer to reference a function, whereas, Bode plots typically refer to a system. Right? So they tell you the frequency characteristics of a system. Here we're talking about the frequency characteristics of a signal.
Okay.
So it's similar but different.
All right.
Okay. Let me do a little bit of MATLAB for you, I think, in the last 10 minutes. Let's see if we can make this work. Okay, so when we, I guess we'll do the, we will start the Euler's formula stuff on Friday. Yes.
I signed up for the lecture when I registered for the class.
Yes.
So, like, did everyone just automatically get the Monday one and then we have to select?
You mean the recitation?
Yeah.
No, there's two separate sections. And whichever one, the one you register for, is the one you have to attend. Although this Monday is going to be holiday. So John's going to be contacting you. We're going to try to get all the Monday people to show up to the Wednesday one for this week only.
Oh, okay.
Because otherwise there is no recitation.
So we missed the recitation.
I'm sorry?
We missed the recitation on Monday.
You're,
Didn't have,
this week? No, there are no recitations this week.
so you're trying to make up that.
Right. I'm talking about following, the next week's recitation. Okay. Can you see anything? You can't see what I see. Hi, can I help you? Okay, now's not the time. Why don't you have a seat and we'll talk later. Oh, here we go. Laptop. Send a... Yes.
Those who have Wednesday recitation, is there one today?
No, they start next week. Can you see anything yet? Come on. You see blue?
Yeah.
All right. I swear this thing gets more finicky every semester. All right, let me know if you see anything. Survey says we're wasting valuable minutes. Really?
That's UVGI.
That's because I put it in the wrong one. There we go. Awesome. Okay, so let me, let's do this. Let's look at a simple cosine. So I'll post this code online. Don't fret too much about it, about trying to copy it down. And is that big enough to read? Yeah, it is. Okay. So let's go ahead and create a cosine like the one we did on the board. So let's see. T equals. So I don't know. Should we make a frequency of 4 hertz? Okay. And let's see, how many seconds should we draw the plot for? 10 seconds? If I do 10 seconds, how many periods are we going to see? 40, right? Each second gives me 4 periods. If I do 10 seconds, I'll get 40 periods. It's going to be a bit crowded. Let's do 2 seconds. I think 2 is good. So what I'm going to do is I'm going to say lin space 0, 2. So the lin space function says create a vector of numbers that starts at 0 and ends at 2. And I think by default it gives you like 50 values. And if you want to override the default, you can say I don't want 50 values, I want like 1,000 values. So when I run it, you can see that it's created for me 1,000 values. And I bet for you that the first value, if I say what is t of 1, oh really? How the hell am I supposed to fix that?
That's the first value of 0, right?
That's the first value of t is 0. I'm just trying to figure out how to get it so you can actually see that. Okay, I guess I'll have to calibrate the screen next week. Or no, oh, what does this button do? That button does jack squat. Okay. All right, well if I look at the first value of t, let's try it like this. Yeah, I know that. Okay, so my first value of t is 0. And then I get 1,000 values of t. They go all the way out to t equals, if I went to the last one, it should be 2. So it's got 1,000 evenly spaced values between 0 and 2. Okay. And x equals cosine 2 pi f t. So if I run that, now you can see that I've got a variable x that has just as many values as the variable t. So t has 1,000 digits. X has 1,000 digits. X is the cosine. Now I can just plot them. Plot t comma x. Okay, so am I seeing what I expect? Okay, it's a cosine. Okay, what is the amplitude 1? Yeah, that works. What's the frequency look like?
Looks like 1/4 of a second.
Right, there's two ways we could think about this. We could either count how many repetitions we get in a second. So in a second, I get 1, 2, 3. I get 4 repetitions in a second. That's 4 hertz. Alternately, I could look and see how long one repetition takes. How long does one repetition take? About 0.25. That's pretty nice. All right, I like that. If I want, I can select the arrow and right-click, and it gives me a whole bunch of options. I can, like for example, I can turn on the grid. That's pretty cool. All right, let's go ahead and park that over here. All right, let's add some phase shift to this. See, phi equals negative 1. So again, my generic cosine, 2 pi ft plus phi, where phi is negative 1. So am I going to get a right shift or a left shift? I'm adding a negative value. So it's net minus, it's going to shift to the right. How far to the right am I going to shift it? Remember, it's phi over omega. It's phi over omega. So phi is 1, or negative 1. Omega is 8 pi, 2 times pi times 4. So I'm shifting it to the right by 1 over 8 pi seconds. What is 1 over 8 pi? I don't know. Let's find out. 1 over 8 times pi, 0.04 seconds. So not too much, but we should be able to see it.
What's that little window?
Yeah, let me introduce you to the windows. So this window up here is called the editor. I'll do like a whole lecture where I explain this in a bit more detail. But this is basically just a text file where I type commands. And then you can execute all the commands in the editor and it'll do them all at once. This is called the command window. It basically lets you type in commands one at a time. Instead of saving them all up in a file, you can just enter them one by one in the command window if you like. All right, so if I plot this, let's pay attention. Is it going to shift to the right? Did shift to the right. Okay, did it shift to the right by the amount that we expected? 40 milliseconds? It's kind of hard to say. Here's what we could do though. You see this button right here, the data cursor? I'm going to select the data cursor and park it right there, and I'm going to shift it till it gets just up to 1. Okay, so it's telling me that x value is 0.04 and change. And is that where I was expecting it? Pretty good. Why not exactly? Pixels. What do you? Not pixels. Not enough points in what? In the graph, right? I only have a resolution of, I only put 1,000 points in there. So there's only like the true value of where it maxes is this. But I've only picked 1,000 points. So I may have a sample just before there and just after there, and that's the closest one. If I wanted to get it exactly right, the easiest thing to do would be to add more points. Right? So if I wanted, I could come back and say, screw 1,000 points. I want 10,000 points. Right? Make that plot. Okay, now if I come and put the data cursor on there, well, first thing is going to take me a little longer to drive right up to that 0.0390. Okay, a lot of moving pieces to this. Okay, so I think when we come back on Friday, we're going to do this example a little bit more. We'll talk a little bit more about MATLAB, and then we'll get into the Euler's formula business. Okay? Keep reading the book. I'm trying to follow it closely. If you have any questions, I'll be around for a couple minutes, but then I got to go teach upstairs.